Hello everyone. I'm going to first spend, I'm not in the right account here. First I would like to show you a couple of unrelated kind of topics to the main thread of this lecture. So the first thing is several people have asked how to obtain the course content locally on their personal computers so that they don't have to be connected to the internet to study. So first of all, we currently don't have a solution set up for you to download the videos. I am going to be working on that, and as soon as it's available, I will let you know. I understand many of you don't have access to internet at home, so I will be working on trying to make the videos available to you for download. To download the course content, you can do the following. Watch very closely. You will go to New, open up a terminal, and it will show you this. This is called a terminal emulator. It's like a Unix terminal or a bash shell. You can use the ls command to see what's in the directory. The data course directory contains all the course contents. What we will do is zip the data course directory. So you will say zip-r datacourse.zip data course. So this is going to zip up data course into datacourse.zip, and the -r means that it will include everything that lives under the data course directory. And you'll see a lot of text fly by saying adding, adding, adding. And if we look back at our directory structure, we now see datacourse.zip. And you can click that. Saving disabled. Well, here we go. So I'm not sure exactly. Usually clicking on this works. But what you can do is you can click this check mark and an option to download will pop up. And then that will download to your local computer. You can unzip that on your personal machine. And then you will see inside your data course folder with all the different notebooks in it. Now, to actually run those notebooks, you will need Jupyter on your computer. Jupyter is included in what's called the Anaconda distribution of Python. You can go to anaconda.org, download Anaconda, and download the version of Anaconda appropriate for your operating system. Remember, we are using Python 2, so you'll want to download the Python 2 version. Once that's downloaded and installed, you will start up Jupyter based on whatever makes sense for your operating system. So for Mac OS, you'll go to your applications directory, and there will be something like Anaconda or Anaconda Navigator or Jupyter, something saying Jupyter or Anaconda. And I trust you can figure it out to launch the application. For Windows, in your Start menu, there will be a folder for Anaconda, and there will be a Jupyter Notebook button. So what you're looking for, generally speaking, is kind of a button in your applications that lets you launch Jupyter. You can probably Google and learn for yourself how that's done on your operating system. On Linux, like me, it's actually just in a terminal. I just launch Jupyter Notebook. And that opens a Jupyter Notebook server in my browser. And I can navigate around my operating system, my file system, and go to whatever I like. So I'll go ahead and extract data course. So here's the data course that I downloaded from Jupyter Hub onto my machine. And I can open up the notebooks and run them. So this cell just ran. Now, a couple of words of warning. First of all, you cannot submit solutions to the grader from your local machine. Our grader is on the internet and will only accept solutions from Jupyter Hub. So you cannot work on the mini projects locally, but you can study the lecture notebooks. Additionally, not everything in the lecture notebooks is going to work in your personal Jupyter Notebook server. You may need to install packages using Conda or pip. I'm not going to get into how to do that right now. I'll show you that at the conclusion of the course. I don't want anyone to feel emboldened to mess with things on Jupyter Hub that might result in breaking your environment, which we will not fix for you. There's 500 of you. There's simply not enough of us to be managing everyone's environment if you start doing things that break it. But that will get you started on studying on your personal machine without the internet. I will probably, once I have set up video downloads, I will send an email with instructions on how to do the video downloads and instructions on how to do the things I just showed to use Jupyter on your local machine. So I'll go over this a couple more times. Again in email, another time in email at the conclusion of the course, and again demonstrated at the conclusion of the course. The other thing I wanted to show is I wanted to talk a little bit about the PW Mini project. So some people are getting started on the PW Mini project, and I briefly showed this in an office hour and in the last lecture. But I wanted to mention a certain strategy that I hope everyone uses, which is I really hope everyone thinks about what this data means and tries to interpret the data and use their intuitions about it in order to check what they're doing and make sure what they're doing makes sense. So there's a lot of information in the notebook about this data. We say the data comes from the Britain's National Health Service. So this is all medical data. We link to a glossary of terms and an FAQ about the data. We explain what the different fields of the scripts variable mean. We explain what the practices variable mean. And we have little examples here where we've just displayed the first two elements from scripts and practices. So the scripts are about prescriptions issued by practitioners, medical practitioners, or dispensed by pharmacies, I guess. There's information like the name of the dispensed object, whether that's a medicine or some kind of bandage or other medical instrument, the quantity that was dispensed, the number of items, sort of like the number of refills, the cost of the ingredients, and the practice that was dispensed from. And thinking about these things are going to help you a lot. So for instance, like the net ingredient costs we see can be like a few pounds or tens of pounds, maybe even hundreds of pounds. But you probably aren't going to see a net ingredient cost of 100,000 pounds or even 10,000 pounds. So if you are calculating something like the average net ingredient cost and you get an answer like 1 million, probably you've done something wrong. And it's going to help you a lot if you make sure to actually think about these bits of information as meaningful bits of information and not just numbers or strings. So please, please, please think about the data, think about what the individual fields mean, what the objects mean. So like these dictionaries correspond with dispensed pharmaceutical items. These correspond with individual medical practices. So try and get a feel for the data. Try and develop some intuition about what to expect as answers, what the data looks like, what the distribution of costs are, what the distribution of items are. Don't just blindly try to write code that does, what is described in the question. Use your awareness of the data to guide your solutions. If you don't, then you are going to have a really tough time understanding the questions and coming up with adequate programming solutions to solve them. So I just wanted to emphasize that, since many people are starting on this now, or not many, but some people are starting on this project now. Okay, so with that said, I'm going to turn to the actual lecture content. I'm going to cover now the last notebook in the Python section. The only one we haven't gone over now is this WQOOP notebook, which stands for Object-Oriented Programming. So I briefly mentioned this in a previous lecture, but pretty much I say object a lot when speaking about Python. And that's for a reason, which is basically everything we interact with in Python, including functions and files and numbers, like integers, these are all objects. And objects have methods and attributes. Attributes are kind of the information that characterize an object. Methods are things we can do with an object. So, for example, I might have an object called a bike. And a bike has attributes like the number of gears. It has attributes like the height of the bike, the size of the wheels. These are all bits of information that describe or characterize the bike. And additionally, there are things I can do with the bike. I can steer the bike, turn the handlebars. I can turn the pedals to move forward. I can apply the brakes. I can change the tires, remove the wheels. I can do all kinds of things with the bike. These are methods, actions I can take, functions that belong to the bike, functions that are done with the bike. So that's methods. We've already made use of these a lot. So for instance, we've used the get method of the dictionary. We take a dictionary, we do .get. So get is not generally a function that we just use by itself. We use the get function belonging to a dictionary. So it's the get method of the dictionary. So an object is basically anything we can store in a variable, or anything that has a name, really. We've looked at objects with different types, integers, strings, dictionaries. We've looked at all of these before. These types are indicative or indicate what class an object is. So objects are of a particular type or of a particular class. So there is a string class, an integer class, a dictionary class. And class is a bit more of a bit more full idea than type. A class is sort of a blueprint for an object. It's where we define what the attributes and methods of an object will be. Some more examples. There's complex numbers with real and imaginary parts. So if x is a complex number, that's 5 plus 3i. We can get its real and imaginary parts by looking at its attributes. It has a real attribute and an imaginary attribute. Some strings have some methods. So we could use the lower method of a string to print it out in all lowercase. We could use the upper method to print it out in all uppercase. Anytime we are accessing the attributes or methods of an object, we do that with this dot notation. Just like we saw when we talked about importing modules and talking about namespaces, we used pd dot or np dot. It's the same with objects. We access that object's scope that object's namespace by using a dot, and then we can refer to all the internal functions and variables of that object. Internal variables are just attributes. Internal functions are just methods. They are defined within the class of the object. We'll typically interact with an object's methods more often than its attributes. The attributes characterize the object, and usually to mutate the state of an object, we will usually do that via its methods. So for instance, if I was looking at my bike, its one attribute might be its color. I have a white bike. Now, if I wanted to change the color of my bike, I can't just decide my bike is blue. What I would have to do is paint my bike. So I would use my bike's paint method to change the color of the bike. I wouldn't just change the color directly. I take some action that changes the state of the bike. And that's typical of a lot of objects in Python. Not all of them, but a lot. Often we will use a method to mutate the state of an object rather than change attributes directly. However, we may access attributes just to get information, just to find out what is the state of the object. So for example, if we make a complex number, we are not allowed to alter the real attribute of that complex number. It's a read-only attribute. Now, something like this is relatively rare. Usually, we're not locked out from changing attributes of an object, but it's usually discouraged. Usually, we are given a method for mutating the state of an object. An example of a method that mutates an object is append for a list. So this is one way to mutate a list, and we're given a handy method for that. If we want to find out what the attributes of and methods of a class are, there's a dir function that will show us the various attributes and methods. So we can do that either on an object or a class. It works the exact same either way. Here, I've just truncated the results. Usually this list is fairly long. There's 64 attributes or methods of an integer. So I've just shown of a complex number. So I've just shown, no, this is an integer, sorry. Yeah, so I've just shown the last 6. Another way is if we do x dot and then hit tab, we can get an autocomplete. And interestingly, there's only 6 here, but I just said there were 64. Where are the other ones? So many of them are hidden. All these ones with double underscores, which is most of them, are hidden. And I'll talk more about those later. But they're really not intended for us to use them directly. So if I do x dot and hit tab, it shows me what kinds of methods and attributes I could access from that object or that class. So if x were, say, a complex number, we could ask for its conjugate. And we see that in this list. Of course, even better than dir is to just look at the documentation. So often we will turn to documentation to learn how objects work, especially complicated objects defined in third-party libraries. We often won't be able to figure out how to use an object just based on looking at its available methods and attributes, and instead we'll have to read about it in the documentation. So there's a lot here about different methods of integers and how integers work. Built-in data types tend to be a little bit more opaque because they interact with very low-level elements of the programming language. So the documentation tends to be a little bit more difficult to understand because it's dealing with more elementary operations, closer to kind of the machine. More complex objects, when we go to look at the documentation, it will be a bit more user-friendly. Okay, so we're almost at half an hour. Okay, so ultimately, where is the information about these things? Where are these methods and attributes decided? I mentioned earlier a class is a blueprint or schema for an object. And the class is where its attributes and methods are defined. So we're going to demonstrate how objects are conceived in Python by working through an example of writing our own class. So we will develop a class called Rational for working with fractional numbers. And the very first thing we'll need to be able to do is to create a rational object. There's a special method called init, standing for initialization, that will help us do this. And we're also going to find another special method called repr, that stands for representation, which tells Python how to represent the object as a string. And our rational object is going to be very simple. It's going to have two attributes, a numerator and a denominator. It's a fraction. And to represent the rational number as text, we're going to return a string with the numerator divided by the slash the denominator. And we see we can make a rational number where we specify the numerator and the denominator, and we can print it out as a fraction. Now there's a lot going on here that I haven't discussed. First of all, to define a class, we use the Python keyword class. And then we have the name of the class, and these aren't the arguments that a class accepts, but rather the class this class inherits from. So we'll talk about inheritance more later on, but the idea is many times objects are related to each other. So for example, I might have a let's see. a class that describes people. People have names and ages, but maybe I want to also be able to describe students. Now, not every person is a student, so not every person object should have things like classes or schools, majors, that's only applicable to students. So I might make a student class that inherits from the person class. And that means the student is going to be a subset of person. And like person, it will have a name and an age, but additionally it might have other attributes and methods. So that's the idea of inheritance. Then we have our method definitions. And these are special hidden methods called dunder methods. Dunder stands for double underscore. We have 2 underscores on either side of the name of the method. And these are special. They hook into Python at a low level. Python, these do special things in Python, basically. The init method is automatically called when we create an object of this class. Anytime we define a class and then instantiate an object of that class, the init method is automatically called. So when we say rational, it calls the init method and accepts some arguments, numerator and denominator, which get set to attributes. Now there's another strange thing going on here. There's this self argument, which is used down here, and it looks like there's 3 arguments for init, but we only gave 2. And this is because self refers to the object itself, and the object is always passed in as the first argument of its own methods. So the way this essentially works is we have rational dot init, and then the object itself, which is like rational or fraction. In this case, I guess it's rational. With init, it's like hard to think about because this is during construction. What I'll do instead is I'll demonstrate this with repr. So we never do this. It works, but we never do this. Double underscore methods are not intended to be called directly. You can do it, you're not forbidden, but basically it never happens. And you see we didn't pass any arguments to the repr method, but the repr method takes one argument, self. So what's going on here is essentially this. The object itself is passed in as the first argument automatically to the function when we call that object's methods. We don't need to have self here. We could have anything. And this would still work just fine. Unbound repr must be called with rational instances first. Okay, I don't know why that didn't work. Oh, it's because I didn't update fraction. Right. So this still works with foo here, but it's an extremely strong convention to call this self. You will never see anything other than self here. Always people use self. So that's an overview of some of the peculiarities of defining classes. Whenever we're defining a class, these will almost always be the first two things we write. Init, to define object construction, object instantiation, and repr, to define the representation. I've been using this word instantiation several times, and it's because we think of objects as an instance of a class. A class is a schema, a schematic, a blueprint. It's a plan. And then the object is one instance of that plan. So for example, you and I are both instances of the species Homo sapiens sapiens. You and I are different. We are different people. But we share a blueprint. We share a species. So we're both instances of Homo sapiens. We're both instances of humans. In the same way, this fraction object is an instance of the rational class. So objects are instances of classes. This is another example of what I was describing before. So we have my class object that is constructed to hold a number, and then doIt just prints that number. And as I said before, whenever we use an object, we use a method of an object, that object is automatically passed in as the first argument of that method. So let's continue building up our rational class. So far, it can print out a fraction representation of itself, but not much else. One thing we might want to be able to do is to reduce the fraction to the, by the greatest common divisor of the numerator and denominator. So what we'll need is a method that computes the greatest common divisor and then divides the numerator and denominator by both of those. And I've split this up into two pieces, a piece that computes the greatest common divisor and a piece that actually reduces the fraction. And we can see reduce is very simple. It computes the greatest common divisor, GCD, and it updates the numerator and the denominator by dividing both of them by the GCD. And then it returns the updated object. So this is very common in classes for certain methods to return self. We could also do this slightly differently, where rather than mutate, so this is a mutation of the object, rather than mutate the object, we could return rational self.numerator divided by GCD, self.denominator divided by GCD, where we would return a new object, a new rational number that's been reduced. but instead we mutate the object and return it. We don't necessarily need to return it, that's just our choice in this case. Now for computing the greatest common divisor, I'm not going to get into the mathematics so much, because I don't think it's really necessary. If you want, you can dig into how the example works. But I will highlight that I have this method I've prefixed with an underscore. So I have underscore GCD. And that's because I don't really intend for this function to be used directly. It's a helper function. It's a helper function for the reduce function. The only time I would really use this is internally within the object when it's called by another method, like here. And the convention in Python for denoting helper methods is to prefix them with an underscore. And in fact, so we see if we do dir rational, we see all the methods and attributes, including ones we didn't even define, but are just by default defined for all objects. But if I take rational dot and I hit tab to autocomplete, it autocompletes with reduce, which is the only method in the class that is not prefixed by some amount of underscores. So GCD, this underscore actually enforces that I won't get this, that method won't turn up in autocomplete. So in some sense, it really does hide this method. So we can put in a fraction 16/32, reduce it, and print out the fraction. We could also put this on one line, since reduce returns the fraction itself. So our rational class is getting more functional, but we can't do math with it. If we try and do 4 times fraction, we get unsupported operand type star for int and rational. Just like if we were trying to add a number to a string. Same type of error. So we have to tell Python how to actually implement these mathematical operations. And if we look at a class that has the capability of using those mathematical operators, we see a hint of how we might do this. There's add, div, mul, and sub. So those are addition, subtraction, multiplication, and division. And by implementing these methods, we can tell Python how to interpret these operators. So when we use these, they're actually calling methods of objects. When we do 1 plus 1, what this is doing is 1 dot add 1. Well, at least it's doing something like that. Let's see here. well, I'm not sure why I'm getting a syntax error here. I would expect this to work, but it doesn't. So now I look like a fool, but nonetheless, that is what's happening. A method of the integer is being called when we perform this addition. And the proof will be in the pudding when we implement it ourselves. So we're going to implement add, div, mul, and sub. And just like repr tells Python how to print our object, these will tell Python how to use these mathematical operators with our object. So we'll just implement mul for now. And the way multiplication works for fractions is if we have an integer times our fraction, we'll multiply that against the numerator. If we are multiplying together two rational numbers, we'll multiply their numerators together and their denominators together. Simple enough. And if we get any other kind of number, like a float, or something that's not a number, then we will raise a type error because we don't know how to deal with those. Expected number to be int or rational, got %s. And these return rational numbers. If we were multiplying by a float, we probably couldn't return a rational number. We'd probably have to return a float. So now we can do some math. We can take 4/6 and multiply by 3 to get 12/6. 5/9 times 2/3 gives us 10/27. So this mul method gives meaning to using this multiplication operator. And of course, we didn't write support for float. So that's not implemented. Expected number to be int or rational, got type float. And we also haven't implemented addition or subtraction. Unsupported operand type for plus, rational and rational. So you can see already for this very limited object, which can do very little, we've produced quite a bit of code. And writing classes can be quite a lot of work. Which is why inheritance is so important. Because rather than producing everything anew every time we come up with an idea for a new kind of object, every time we come up with an idea for a new class, we can rather build upon other classes. Already explained this. I'll come back to this. So let's talk about inheritance since I just mentioned it. And we only have 10 minutes left. Yeah, I think I can probably finish this lecture. So, like I said, often we'll want to build off existing ideas in other classes. So for example, our rational class is a number, and we would like it probably to behave like other numbers. And we could maybe write a rational class that uses float arithmetic and just converts between floating point and rational representations during input and output. And then we could have rational inherit from float, and all the internals of rational would be based on float, and then it would just define a repr method that represents floats as rational numbers when possible. and that accepts and object construction maybe works in the way it did before, where we give a numerator and denominator, but then internally we treat that as a float. And then we would be able to get away with, we wouldn't have to define add and subtract and multiplication. We could just inherit all of that from floating point numbers, where all of that is already defined. We do, however, maybe pay a price in terms of the complexity of converting between floating point and rational representations of numbers, especially because not all floating point numbers can be expressed as rational numbers. Well, all floating point numbers can, but not all real numbers anyway, which is what floating point numbers are intended to approximate. So let's see an example of inheritance. We'll define a rectangle object with a height and a length, with area and perimeter methods. And we can make rectangles that have an area and a perimeter. Very nice. And maybe we would like to define as well a square object. Now, square can inherit from rectangle because these two things are very closely related. A square is a subclass of rectangle. It's a type of rectangle. And rather than write out area and perimeter methods all over again, or even fully defining an init method, what we'll do is we'll define an init method that simply uses the init method of the superclass of square. And now this initialization method will only take a length, not a height and a length, because squares, of course, have 4 equal sides. And it will just initialize a rectangle, essentially, with height and length equal to each other. And then we get the area and the perimeter methods for free. We didn't have to define these at all. We inherited them from rectangle. Now notice S, this square object, is a square, but not a rectangle. The type of S is square, not rectangle. On the other hand, if we're interested in whether S behaves like a rectangle, we might ask if it's an instance of rectangle, which it is. It inherits from rectangle. So S is an instance of rectangle. And often this is what we care about, whether S will behave like a rectangle. So in another lecture, I gave an example where I checked is instance of some input base string. We haven't used base string at all. We never use base string. We never make base string objects. But there are multiple types of strings in Python, all of which inherit from base string. And so if I want to know if something is going to behave similarly to a string, I might check if it's an instance of base string rather than check if its type is string or Unicode string or anything of that sort. So usually if we're doing explicit type checking, we will do it using isInstance. So why would we want to use these things? Again, it comes back to the idea of sort of the modularity of the Python programming language. we want to organize our code into namespaces that group together similar operations. It helps keep our code organized, both at the level of, packaging individual lines of code, like defining functions, as we discussed in the very first lecture, as well as when we go to start combining different objects and different modules in Python. It helps keep clear where functions are coming from and what context we ought to be using them in. So, for example, we'll be using the pandas library quite a lot very soon. And one of its main features is the data frame class. So we can construct a little data frame. It's basically a table, and we'll talk a lot more about these. But the data frame itself has a ton of methods, some of which look pretty familiar to stuff we've done before, like sum. So classes help us define objects that mirror the logic of what we would like to do. It's a perspective called object-oriented programming, in which we view programs essentially as a collection of objects interacting with each other. So, when I go to ride my bike, if I were trying to represent that as a Python program, a person object would use their mount method on a bicycle, and then that maybe returns a rider object or something, and the rider object maybe has some amount of energy as an attribute, and has a pedal method, and every time they pedal, it decreases their energy. And so programs in Python become these interactions of objects with each other, and it categorizes or packages the logic together into these discrete, descriptive logical units that help us maintain a clear idea of what our program is doing. And just to give you an idea before we wrap up, or to wrap up, of what serious classes look like, where people are implementing useful objects that are shared among the entire community, the pandas data frame class definition begins like this. This is just the initialization method, and it calls many other methods like init ndarray and init dict, which are helper methods to help initialization from different data structures. And this is quite long. And it's not even really the whole picture. Not nearly. This doesn't get into any of those methods that we saw with tab auto-completion just a moment ago. But we see it inherits from ND frame. So inheritance is very important. As you can see, classes and class definitions can be quite complex. So the corresponding mini project for this lecture and object-oriented programming in general is the VC mini project, in which you are asked to develop a point class capable of handling simple linear algebra operations in 2D. And it begins by giving you a schematic for a point class where you're asked to define the initialization and repr method and just make some strings. And gradually you fill out the functionality of the class You should be adding in methods to the class to solve the various problems we ask you to solve. So that concludes lecture for this week. I'll see you at the office hours.